1, 2. Good morning. The next talk will be about unlocking filevault, the encrypted file system in Mac OS X computers. All of you Mac users probably know this. Besides the fact that they claim to use AES with 128-bit, it was so far not really sure what was behind it, how it worked. Now Jacob Appelbaum and Ralf Philipp Weinmann had a look into that, and they will present their findings and what they found out, how it works, and what is really done there. Please welcome them and have fun with that talk. Thank you.
So just to start off, we have a wonderful guest performer here who's going to perform a song for us. This is Johannes from Monochrome.
It's so embarrassing, I tell you.
He's wearing an Amish hat that's made in China, but he actually bought it in the Amish village in America.
Yeah.
So he's going to play us a song just to sort of set the mood for our talk.
Okay. Yeah, the problem was I was really drunk yesterday at 2 o'clock in the morning, and Jake Appelbaum came and said, "Come on, I have a talk at 11:30 tomorrow in the morning, and all the people, they have to, like, we have to wake them up. We have to do a little performance for them that you really can, like, dig into cryptography, you know, and stuff like that." So he said, "Okay, we need a song about Apple." And I said, "Okay, I drank 7 Club Mate, so I can't I can't sleep anyway. So I can think about doing a song, and I'm really proud it's a copyright infringement. And actually, I don't even use an Apple, but I thought maybe trying to write a love song for Apple. So that's what came out, and I hope you somehow can enjoy it. But anyways, it will be on the internet soon, whatever. Okay, so I think I have to switch to my media player. Long intro. So close, no matter how far. Just how far. Couldn't be much more from the heart. Forever trusting who we are. Oh fuck, I love Apple. Never opened myself this way. Life is ours, we live it our way. Hey. All these words I don't just say. It's different, it's Apple. Trust I seek and I find in you. Every day for us something new. Open mind for a different view. A corporation called Apple. So close, no matter how far, it's soon over. It couldn't be much more from the heart. Forever trusting who we are. Oh my God, oh my God, oh my God, oh my God, Apple. Thank you very much.
Something only Monochrome could come up with. Thank you. So today we're going to talk about filevault, and I think that the results should be interesting for everyone here. I'm interested to know, though, everyone in the audience, if you use filevault or if you have a Mac or something along those lines, maybe a different disk crypto program, could you raise your hand?
Okay.
So we're going to talk about what filevault is, and we're going to talk about problems that other people have found and that we found with filevault. We're going to talk about reverse engineering on OS 10. We're going to talk about like the non-free disk image framework. We're going to talk about free implementation that we're going to release. We're also going to talk about some of the other oddities of Mac OS 10. And we have a special guest hacker here. This is Hikari. So, very amazing guy. He's one of the founders of TorCon, and we're fortunate to have him here. And he put together his contribution in about, what did you say, about 45 minutes or an hour or something to get it working? And then, not including up until 5 minutes ago. Right. So my motivation and Ralph's motivation for this was that we were pretty much interested in disk crypto. Personally, if you saw my talk last year, you know that I have a sort of like passion for data being secure. We also wanted to protect against theft, so we're really interested in the native disk encryption that comes with OS 10. And everybody uses laptops. I mean, most of the people here using filevault, I assume you have laptops. But it's undocumented, and we wanted to know if it was secure and how it works, and Apple claims, you know, unbreakable, trillions of years, and all that stuff. So on the marketing side, they say, filevault secures your home directory by encrypting its entire contents using the advanced encryption standard with 128-bit keys. This high-performance algorithm automatically encrypts and decrypts in real time, so you don't even know it's happening. Yes, filevault, increased security for your computer. But we actually do want to know what's happening inside. That seems like a good thing. So the internals are not well documented. You can look at the man page for HDI util. The disk image framework is private. You have no source, no headers. It needs to be reversed. And the kernel module stuff is not open sourced. So
what we looked at first was the only documentation around is for the HDI util. This is very good because HDI util has a command that allows you to list all the plugins. Disk images is like a very modular framework, so it consists of different plugins. And so far, the only third-party plugin known that was developed outside of Apple's is a plugin for virtual PC images. Now, there's a front end and a back end. The front end is the HDI util program. The back end consists of basically a kernel module that's handling the attach of disk images and a couple of helper programs such as disk images helper, and HDI ejectd. Now, when you have to go to the next slide. This disk image framework has several backing stores. Backing stores are basically the containers that hold your data. And there's like a CBSD backing store, which is just for normal files that hold data. Then there's like a CRAM backing store for RAM disks and different other things, like a CURL backing store, so you can have like the image on like an HTTP server or HTTPS server. And another thing is you have encodings, and what we will look at mostly in this talk is the C encrypted encoding. That's basically the encoding that does the AES 128 and the other cryptographic stuff. And this C encrypted encoding is the heart of filevault, basically. The other thing is that filevault does not allocate like a static amount of space on your hard drive, but it has a sparse disk image that grows. Now, there's different types of disk images that are supported by the disk images framework. There are like shadowed disk images where you only write back the changes to one image and you have a master image in another container. Then there are compressed images and, and then there are sparse images. Now, to get to the crypto details, when you have like the C encrypted encoding, which is basically the outer layer of a filevault image, like you have an inner layer, which is the sparse image, and you have the outer layer that's produced by the C encrypted encoding. Then all the blocks get encrypted in 4 kilobyte chunks using AES-128. And that is in CBC mode. Now, the IV for each of these chunks is generated using HMAC SHA-1, and the key for there's a key that's used for generating these IVs, and that's the HMAC key. I'll go into where these keys come from in a second, but for now it's just an HMAC key. And basically what you do is you have this HMAC key and you prepend the chunk number to the HMAC key and then apply the HMAC. And that truncated to the first 128 bits gives you the IV for this chunk. Now the keys are randomly generated when you create your file vault, and then they are wrapped in the header of an image. Now this header is, well, it's kind of a misnomer because sometimes it's a header that's in the old versions, like there's version 1 and version 2 of the metadata format. And in version 1, it was actually at the beginning of the disk image, and in version 2, it's at, sorry, the other way around. In version 1 of the format, it was at the end of the disk image. In version 2, it's at the beginning of the disk image. Now, what's interesting is that the wrapping of these AES keys is done using triple DES for some reason. So, in fact, I mean, it's kind of cheating because now the security doesn't only depend on AES, but if either AES or triple DES fails, you're screwed, right? Okay, and what they did when they went to version 2 of the metadata format, which was, I think, in Panther, is they introduced an option for having an additional asymmetrically encoded header. And what this is good for is for a recovery feature. I'll go into that a little later. First, let's look at the normal way you unlock your file image again. So the passphrase for your file image is your normal login password. So if your login password is wrong, is weak, your firewall is useless as well. What they use for deriving the key for unwrapping the other keys is something called PBKDF2. That's a very standard algorithm. It's in the RSA PK CS5 series of algorithms. And they use this algorithm, which is parameterized with 1,000 iterations, which is, well, it's kind of low. But you don't want to wait forever for your disk image to attach, so that's probably why they choose a low number of iterations. And what's interesting as well is that most of the crypto parts are actually implemented in something called CDSA. That's the common. Sorry, it's an architecture for cryptography that was developed by Intel, and this architecture actually is open source, and it's modular as well. So it's like bloat. I mean, there's this huge meta framework, and then you have providers sitting in this meta framework, and there's one Apple CSP provider. And this is also what makes like porting like the reverse engineered implementation kind of hard, because then you have to port all the other crap as well. I mean, CDSA exists on Linux as well, but you'd have to port the Apple CDSA provider. So what we decided to do for the free implementation was we did away with all of the CDSA stuff, and we used OpenSSL instead, because that's much leaner. For performance reasons, Disk Images has its own AES implementation. However, it pulls in the SHA-1 from an OpenSSL lib. So this is kind of inconsequential as well, because I mean they have CDSA, but some stuff comes from other parts. And the wrapping that they've introduced in version 1 of their header format which they've discarded again in version 2, is loosely based around a standard that is commonly referred to as PKCS7, which is RFC 2630. And what is kind of funny about this is they wanted to implement it with a random IV that they store on the drive, and they actually do store this IV on the drive, but they don't actually use it. So it looks like somebody, started an implementation and, got held up and didn't quite finish, and then they ditched it and went to another header format. But all that stuff is open source. The reverse engineering was just the disk images framework. Okay, now to the recovery mechanism. When you enable filevault, you can, or basically you have to set a master password. This master password, in turn, protects a keychain that is in your library keychains directory. And this recovery keychain, it's called, contains one certificate and one private key. And this private key is a 1024-bit RSA key. By having this key, you can decrypt another struct in the metadata that also contains the blob where the encryption password and the HMAC password for decrypting the real data that's in your filevault images is contained. Now, the problem is there's something called the Lenstra-Verhoeven heuristic. And what this does is basically it establishes a mapping between the parameter sizes of symmetric and asymmetric key cryptography. And, well, Apple claims they have 128-bit security, but this, if you have set a master password, is not quite true. Because by having set a master password, you have this 1024-bit key on your drive, which is, this key is not encrypted, right? I mean, it's sitting out in the plain text. I should add, like, filevault is only protecting your home folder. It's not protecting all of the other folders on your file system. Now, 1024 bits asymmetrically, according to Lenstra-Verhoeven heuristic, means 72 bits symmetrically. That's not a lot. Usually, these days, you should have at least 80. Okay, so that we went into already. The headers of version 1 live at the beginning of the file, and the version 2 headers live at the end. And in 10.4.7, they actually made the version 2 headers mandatory for sparse encrypted disk images. That's probably because when you log out, the disk images get compacted. Now, if you think about what happens if you compact a disk image, it shrinks, right? And you have the metadata at the end, and you have a power failure, for instance. Where's your metadata after that? Well, whoops, gone. So that's why you should have it like in the new format. Now, let's look at the gory details. The password header, in principle, is very, very generic. I mean, they could easily swap out the key derivation algorithm. They could swap out the PRNG algorithm that they use for generating temporal keys when you re-encrypt, for instance. They could have different algorithms for the symmetric encryption of the blocks. They could have different modes. They could have different paddings. But they don't actually use that. They just have one C encrypted encoding. And that is, I mean, that statically is AES 128. That's kind of interesting, I think. I'm not sure what future versions of OS X have planned. But what I'd really like to see is Apple opening up the disk images framework and allowing other people to write plugins for it, because then you could theoretically also mount disk images, or rather loopback devices in the form of disk images from other operating systems, so you could have actual interoperability, something that's kind of missing in the market of disk encryption these days. I mean, there's TrueCrypt, which is cross-platform, but it doesn't run on OS X. And then there's PGP disk, which runs on basically everything, including OS X, but it's not open source really. So go to the next slide, please. Reversing the disk images framework was actually quite easy because disk images is C++ code, and when you look at the binaries, you can extract like the full signatures of every method of a class if it's not obfuscated, and Apple has not obfuscated disk images. So all of the analysis basically was done using like OTool, GDB, and the debug output of HDIutil. HDIutil, I should add, has a little debug switch, which is great because when you turn it on, it gives you all of the internal, it gives you all of the internal steps it has done. It outputs you the HMAC SHA-1 key, it outputs you the encryption key, so you can verify that you've actually done the right thing when you've reverse engineered and have written your own implementation. Initially, I thought it might have been easier to reverse engineer disk image framework using something called Boomerang, which is a great reverse compiler, but unfortunately, although it supports Macho, the Macho binary format, which is the default on OS X, it doesn't really work so well with PowerPC code, and after I patched it to work with Intel code, it worked better, but it like bombed out on me in like 3/4 of the cases, so it wasn't really useful for generating more than like 1 or 2 functions from the binary. So, but actually, if you look at the disassembly, if you look at the PowerPC disassembly, it's not that hard to see what's going on because the calls that they make to the CDSA framework are very similar in structure. So once you've figured out one of the calls, you get the hang for the rest of them. You just have to be careful because you have to follow a lot of pointers to the structures, and on OS X right now there are, as I'm aware of, no good reverse engineering tools. There's IDA Pro for Windows, but you can't really use something. There's no similar thing such as IDA Pro on the OS X platform. Now, the results that we have is we have something called filevault decrypt. Actually, that's a spelling mistake on the slide. It should be a V and an F instead of an F and a V. What it does, you feed it an encrypted image, either like a sparse image or a non-sparse, like UDIF image, and it outputs you the decrypted image if you have the correct passphrase. This tool works with both version 1 and version 2 encrypted disk images, so even if you have like an old installation and you want to like transfer your data off that, but you don't have the install media, but another box which runs an open system, you can still get the data off it if you have the passphrase or if you can guess it. What it doesn't do is it doesn't expand the sparse images to a real disk image. This is kind of a problem still because what that means is if you have a sparse disk image, you can't mount that, say, on the Linux, because although Linux has support for HFS and HFS+, well, it doesn't know how to use sparse images. So what's needed here is like another converter that converts these sparse images to full-blown images that can be mounted. But that is fairly trivial from what I've seen. The code is very rough at the moment. For instance, it doesn't do the recovery thing yet, but we're working on that still. The code works, and it will only get better. What we also showed is that the cryptography of filevault does not only depend on AS128, I'll reiterate that again to make the point, but it also depends on triple DES, which effectively has only a bit, an effective key length of 112 bits, and on the security of RSA 124. So if either of these three folds, you're screwed. The other thing that's bugging us about filevault is that we'd actually like to have full disk encryption, not just the home directory, because there are a lot of applications that spit all over your file system, like into temp, most often. But also have a look around what you leave behind in var log or in system logs, and then think about, well, if you do something compromising, I'm not sure how many people are in the audience that are, extra legally active. Basically, you might put information into areas of your disks where the police or other agencies can find them if they seize your laptop, and that's not such a good thing for you. So we'd like to have the full disk encrypted. This actually is possible using the disk images framework because it has the CDF backing store, which allows you not to have a file as the container, but a whole device. Unfortunately, it looks like it's not possible using just the HDI util, so you have to hack something up that makes use of the framework by generating headers for yourself, or you have to wait for Apple to do that for you. So maybe the next version has support for full disk images. I've heard that it has recently become a requirement in, maybe Jacob can say something about that?
So I guess recently there's been a presidential mandate this summer from our glorious leader about full disk encryption for all federal government computers. So this could be something that potentially would be a big market for Apple if they were to fix this and open it up. Maybe. It's possible.
Okay. Another thing that you have to look at when you look at any kind of cryptography, obviously, is you have to look where your randomness comes from. Now, with OS X, it's kind of funny, because OS X uses a very well-known and very reputed random number generator called Yarrow, but they heavily modified it. What this means is, usually in other operating systems, you have the kernel collecting entropy throughout the course of the day from various sources, like from interrupt activity, from the number of pages you swap in and swap out. Oftentimes you actually have a hardware number generator. Newer Intel Macs have, or all of the Intel Macs have hardware number generators in the CPU. But from what it looks like, the implementation that they've chosen doesn't utilize any of that. It just gets the entropy from the system time. And how they do this is kind of backwards, because they have a security server, that's what it's called, running in the user space, which feeds entropy to the kernel by writing to dev random. Now, this security server, in turn, gets this entropy from where? Oh, the kernel. And they do that through a debug interface, which is, I think, kind of funny. They do that every 15 seconds. So I'm not saying that that this design can be broken easily. I actually think it's quite hard to come up with a practical attack against it. But I still think it's not very beautiful, and you'd have to think hard about it to justify it, actually. I'd actually like a reason why they did that. And the other thing is that reseeds are done periodically, And these receipts are shorter than it looks because when you look at the when you first look at the source code, it says 50 ticks. Now, you'd expect that 50 ticks are something like 50 times 100th of a second, but it's not. It's actually 50 millisec. And initially, when your system boots up, before it's getting fed entropy from security, the initial entropy comes from the system time, and it does just one reseed. So until security comes up, your random number generator is not strong. I'll leave it as an exercise to the listener to find things that get executed before security comes up and feeds entropy to the kernel. Okay, let's go to the next slide.
When looking through the kernel, which you can easily get from Apple, you get some really great quotes, and these three are excellent. They're really strange quotes. I like how they explain what an IV is, and then they go on to talk about how they didn't want crackers to find their encryption patterns too easily, which I think is kind of funny. In addition, they also talk about how they don't lock memory pages in certain circumstances, but what's interesting is that we know that Apple actually doesn't lock memory pages in almost all circumstances. But here they just give an example of that. And curiously, they also have some problems where 192 and 256 magically just don't work. And they don't really say why that is. But that's interesting. So Maximilian Dornsiff, who I don't think is here, but it would be great if he was, he did some really excellent research on DMA attacks using FireWire. So pretty much anything that has a FireWire device is vulnerable to this unless you either patch the kernel or on PowerPC you can enable open firmware. At the Meta Lab in Vienna, Austria, there's a hacker by the name of Angelo Laub who gave a talk about how to secure against the FireWire DMA attacks. It turns out that on the Intel chipsets, you actually need to patch the kernel in order to fix this problem. He did that and provided the source code for doing that along with a compiled kernel module, though I would probably compile it myself if I were you. And I linked that in the slides as well. But you should obviously be aware of this attack, and it is real, and it is probably possible that if someone's charging their iPod, they might also be dumping your memory if you have FireWire on your box. Again, I talked about this last year, which is the swap files and memory issues, which is basically you need encrypted swap to do disk crypto correctly. And until essentially 10.4, you didn't really have the option of encrypted swap, which basically meant that your passwords would get swapped out to the disk. Unhashed passwords would get swapped out to the disk. So basically no work whatsoever to recover the passwords. And so if, say, there was any type of exploit on your box, or if you have an airport card maybe in your box, I hear there might be some problems with the airport firmware and the drivers, you could possibly go ahead and look for keys that way too. So it's definitely something to keep in mind, and I don't know how the internal is actually, like the internals of this is actually implemented, but in loop.AES you have keys with the bits being shifted around so that you don't leave basically a trail in your memory. Peter Gutmann wrote a paper about this where if you have your key in memory for a long period of time, it oxidizes inside the memory cells. And I don't know if they do that or not, but it would be interesting if they opened this up so we could find out if they do. Because it seems like there are a number of things that if they've done that wrong, that could be another vector, though that's probably not a vector anyone here really cares about. But if you do, you probably aren't using this. As an example about how, I mean, everyone knows we need to encrypt our swap, right? But if you were to go to apple.com right now and go to /macOSX features filevault, they have a nice image on their page titled security, and you'll note the use secure virtual memory is unchecked, which is excellent. So apparently Apple, even when talking about security, neglects to mention that little problem. Something that I haven't heard anyone else talk about. Ralph and I were talking about this, and essentially, if your laptop runs extremely low on power, you're going to have your memory contents written out to var VM sleep image, and it's careful. However,
it's not quite careful enough. So if you have encrypted swap on, the contents of the sleep image will be encrypted, but you're not actually asked for something like a passphrase when you boot up again. So what happens with the key? Well, guess what? They write it to the disk. So this is not really useful. I mean,
if you wanted to attack one of these laptops, not one of these, please, but if you wanted to attack one of these laptops, it would be possible to simply unplug and just wait. So obviously another vector here is weak passwords. So brute forcing is nothing special, though until a couple of days ago, neither of us had seen any brute forcing programs out there, other than I'd seen a bash script that someone used. They just wrapped it around HDI util, which is not particularly interesting. Then, was it like 4 days ago?
Yeah.
Ralph found actually brute.dmg.c.
Yeah, that it's it's written by an as of yet unknown person. Well, we have like a hint of who it might be, but so far he hasn't answered. And this is a program that allows you to brute force version 1 the images. So it will not work on the current filevault images, but it will work on older versions. Like if you would be running 10.2 or something like that and had filevault enabled, or actually, yeah, if you had encrypted disk images there, it would work on them, but not on the ones on Panther and App. So
yeah, so we mentioned previously that we had David up here, and he was able to implement about 200 keys a second running on his Sempron 3300. And that's kind of nice. I think previously we were getting about less than half of that.
Yeah. It was like 50 or 60 with the brute DMG.
Can you speak into the mic?
According to the brute DMG program, they were saying they were getting about 50 to 60 per second on their, I'm guessing their PowerBook or something, or MacBook Pro, something like that.
So David here is going to demo a program that he wrote in an amazingly short amount of time, and it's a filevault crack. So if you want to give it a shot, we switch to his laptop, please.
It works. Okay. So yeah, the whole story behind this was that I met up with these guys a couple days ago when I just got into town, and they were explaining how all the stuff worked. And they mentioned that it uses PBKDF2, and the WPA cracking stuff that I have uses PBKDF2 as well. And so it just uses a higher amount of iterations. WPA uses 4096, and this uses 1000. So I was like, oh, I could just modify my FPGA stuff and get it to work really quickly. So I modified my FPGA stuff and implemented a cracker using their source code. And so I'm going to demo that right now. So right now you can just run vfcrack on your normal PC. And I just have this dictionary file, which just consists of a bunch of different passphrases that you want to try. And so all you do is give it the dictionary file and then whatever disk image that you have. And so this one's using the version 1, and it's going through at about 200 per second. It should find it in a little bit. But all this is doing is just running the PBKDF2 and then checking the header to see if everything works properly. And so there, it just found the passphrase, which is 1, 2, 3, 4, 5, 6. And so I was like, wow, this is kind of cool. Let's see how fast it runs in the FPGA. So I have this shell script that swaps over the FPGA to the special image that I made. So this is reconfiguring the FPGA on my laptop, which is actually a compact flash card in my PCMCA slot. And now it's running this code that is basically, the chip is accelerating PBKDF2 cracking. So now all I have to do is basically feed it over the same arguments and specify which FPGA I want to use, which is the only one that I have in my system. If I had multiple ones, I could use different dictionary files on the same DMG file on different FPGAs and split it up that way if I wanted to. But this one will just run on the one on my laptop. So right now it's going through at about 2,000 per second, and it just found it. So this, running on this little compact flash card, cracks this stuff about 10 times faster than a laptop. So if I had 10 laptops here, it would be about the same speed. This also works with the version 2 format, which I just got working about 5 minutes before this talk started. So here's a second image with the version 2. This has a different passphrase. Just running on my PC right now. And there, the passphrase is filevault. And then I can also run that on the FPGA and it does everything properly. So that's my portion, I guess. Yeah. Thanks a lot.
We could switch back to the other. Great. And of course, he did forget to mention that he has a cluster of 16 of these sitting on your desk or something?
Yeah, 15.
Yeah. Of the FPGAs, right? So that's a pretty excellent improvement over about 70 keys a second. So got some other references in here. If you happen to be the author of DMG Brute, it'd be nice to meet you, talk to you. And it's all going to go up on crypto.nsa.org/vilefault shortly. Actually, probably during questions, I'll copy it over. We'd like to thank these people for their help and for their input. So thank you all, especially to my lawyer, Jennifer Granick. Our lawyer, I guess. And every person at the EFF, thank you in advance. And everyone at the CCC. And also Club Mate. So now I guess is the time when we can take some questions, if anyone has any questions.
Okay, I'm sorry by advance because I'm going to try to talk cryptography early in the morning. So it's just, you didn't mention about the security of filevault. You talked about, I think you know about it, but you forgot to talk about the eventual weaknesses of the chaining mode, which is CBC, and I think there is some kinds of attacks on CBC. It was talked about a lot in LopAOS or NDMcrypt some times ago. So yeah, you forgot about it, and maybe there is a reason, or I don't know, but I think there is some weaknesses on CBC which could lead as well to failure in filevault.
Actually, using CBC is fine as long as you have a large enough block size. So the attacks that you usually have on CBC mode is that you have collisions, basically, that happen when you have small block size. Say you have DES and you have a 64-bit block size, then it wouldn't be a good idea to use CBC mode because you'd have a collision with a probability of 1 to the minus 32. However, for 128-bit block sizes, the probability of that happening is rather negligible. You could, of course, use other modes as well. I mean, one of the modes that you could use would be counter mode, but then you'd be kind of screwed because people could arbitrarily flip bits in your blocks, and you wouldn't know. So that's kind of a bad idea. The only thing that would really improve the security over CBC would be to switch to something the disk encryption modes that have recently been discussed and proposed in the IEEE working groups, but those are not standardized yet, as I understand it. So, well, what this comes down to is that actually Apple doesn't have much to be ashamed of cryptographically. I mean, they have a couple of slip-ups, but none of them turned out to be like devastating. The iteration count could be higher, for instance. I've mentioned that already. Parts of the source code read like they couldn't really keep the different PKCS standards apart. Like in some sections of the CDSA or the CSSM source code, there's like a comment about a PKCS1 padding where it's actually, well, PKCS1 is asymmetric, and they're talking about symmetric stuff, and it should be PKCS7 in that case. But in principle, they've stuck with well-known standards, and they have avoided some attacks as well. I mean, it's good that they use IVs that depend on the block number, actually. I mean, they could have done worse. They could have just had a counter. So the security of filevault is, as of now, as I see it, is holding up pretty well, except for attacks that exploit the implementation or that exploit data leakage outside of the actual container. And of course, passphrase cracking. I also don't think that you can do much with the theoretical, I wouldn't say it's a vulnerability, but the theoretical problems that you have with Yarrow. I mean, because the security server is feeding the kernel entropy through def random, other processes can do that as well. They can, I mean, you can write like a huge chunk of zeros into your entropy pool, and this doesn't even work if you're not root. But it doesn't compromise the system, and this shows that Yarrow is kind of a robust design, and it also shows that Apple has made a good choice in choosing Yarrow, although they maybe should have modified it a little bit more, more elegantly, let's put it that way. So I hope this answers your question. Okay.
I have a question over here.
Okay.
Over here. To your left.
Oh, okay, sorry.
So there seems to be recently a lot of backlash against researchers looking at Apple stuff, as we saw by the wireless driver stuff that happened. I was wondering if any Mac fans have contacted you, or if you expect to receive any emails or anything of the sort.
Oh, okay.
Oh yeah.
I actually received an email a couple of hours ago. Can I?
Yeah.
I hope he's not in the audience. Okay. So I should translate. Basically, he's asking about the lecture that we're giving here, and he's stating that he's an Apple user himself, and asked what we want to show in this talk. He asked whether it's insecure. He asked whether, whether one should use this technique. Of course, I haven't replied to this mail yet, so of course, yes, Gunnar, you should use this technique. And he's complaining, I mean, he doesn't know what we're talking about, but he's complaining that we always show attacks here. I mean, what the? And he's asking whether we basically want to spread FUD. I mean, Sorry, you look like a typical Apple fanboy to me. I mean, I like Apple products, but I can also be critical of them. And I think this is not, I mean, this is not only, this can only be seen with Apple products, but with Apple products, there's a huge amount of users that get very, very protective of their operating system and of their PowerBooks or MacBooks or whatever it is. For me, it's just like a piece of technology, and I chose it because it was good at the time for what I wanted to do, and that's it. Yeah. Yeah, well, I didn't write it, sorry. Okay. More questions?
Okay, here in the back, in the middle. I just comments on the question one before. There is a problem with the constant initialization vector per block, which is theoretically just a cryptographic, malpractice.
Wait a second. It's not constant per block.
Once you choose your key, it's
yes,
constant. So for your container, it's always the same, whatever you write into the block.
That's correct.
And the second point is the bit flipping attack is in general also possible with CBC mode. The CBC mode doesn't protect the integrity of the data.
That's correct as well. Yeah. Okay, so this wasn't really a question, but thank you for adding to the content of this talk. More questions or comments?
We should put up the source code now, I think.
Yeah.
Do you want to commit me? Do you want to unplug and commit that?
I just wanted to say there is a little tool called class dump,
Yes.
which lets you dump a header file from an Objective-C class. You can use that tool on the disk image framework itself, and there's coming some interesting stuff out of it.
That's quite correct, but have you actually done that? Have you looked at the output?
Yes.
Okay, what do you see? Because the thing is, although there is a little bit of Objective-C for the glue code, most of the stuff is implemented in C++. And you just see, when you use class dump, you just see the methods that allow you to connect to the framework, and you can't actually see inside.
Yeah, that's true.
Okay.
But still interesting, though, I think.
Well, maybe. Okay. More questions? Did we disappoint you? Did you expect filevault to be completely broken? Can we have a vote on that? How many of you came here expecting filevault to be totally broken? Okay. Okay, we got to try harder then.
So the source code will be live in about 5 minutes. Crypto.nsa.org.